Today's electric vehicles are incredible feats of engineering, but their ultimate capability is bottlenecked by the chemistry sitting inside the battery, specifically the liquid electrolyte, the fluid that allows energy to flow back and forth. Because it's a liquid, it is highly sensitive to extreme physical environments. For the average driver, this liquid chemistry creates a very real daily friction point. We constantly monitor range depletion, and when the battery inevitably drains, we're often tethered to bulky charging hardware for 40 minutes at a highway rest stop. Add environmental stress, and the liquid inside those batteries degrades even faster. In regions like Rajasthan, where summer heat blasts the pavement, the liquid electrolyte struggles to dissipate heat, reducing daily efficiency and long-term battery lifespan. Head into the mountains, and you face the exact opposite problem. In sub-zero temperatures, that liquid core becomes highly viscous. It thickens up, and its ability to hold and transfer a charge slows to a crawl, sapping driving range before the car even moves. But the timeline for these hardware limitations is closing. By 2026, an incoming wave of stable battery chemistry and predictive artificial intelligence is set to change how these machines operate, bypassing the physical constraints of the liquid-ion era. This diagram compares standard and solid-state cells. By replacing the liquid core with a rigid solid-state electrolyte, energy density leaps to 500 watt-hours per kilogram, doubling capacity. This translates to a 1,000-kilometer range and a 10-minute rapid charge from 10 to 80%. At the same time, another chemistry is entering mass production: sodium-ion batteries. Sodium is incredibly abundant, extractable directly from the ocean, bypassing the supply chain bottlenecks and high costs of mining lithium. Sodium-ion cells perform where lithium struggles. They hold charge in freezing winters and resist degradation in extreme heat, making them ideal for varied climates. By stabilizing the internal chemistry, engineers have built a hardware foundation durable enough to support demanding software and direct integration with the power grid. With the hardware solved, the focus shifts to the dashboard. Google is rolling out an AI-powered EV ecosystem designed to be the software brain that maximizes these massive new batteries. This map interface calculates your trip by injecting parameters like vehicle weight and battery capacity into the route line. It then cross-references 3D road elevation and live weather overlays like headwinds to adjust your predicted charge level accurately. This predictive routing provides the precise data required to manage a vehicle's energy state, narrowing the gap between driver expectations and actual remaining range. That data management extends beyond software directly into the physical infrastructure around us. We are already seeing static wireless charging pads, allowing cars to align over a magnetic ground pad and charge without a single physical cable. This diagram shows dynamic wireless charging. Transmitter coils embedded beneath the asphalt project energy waves to a receiver on the vehicle. Recent pilot programs demonstrate commercial trucks maintaining a 99%. Domestic manufacturers in India are also preparing for this bidirectional future. Companies like Tata are rolling out vehicle-to-load systems, embedding the hardware required to turn consumer cars into active power distributors. Dynamic charging and V2G reverse a traditional relationship. Cars are moving from passive energy consumers to mobile energy distributors that actively support the grid. To manage hundreds of millions of these mobile distributors, governments in major markets like China and India are rolling out the final layer of this ecosystem: mandatory battery traceability IDs. This flowchart tracks a battery's life cycle using its new digital passport. The unique ID tags the cell at the factory, logs its usage data inside a car, tracks its secondary life powering a local grid, and follows it to a specialized recycling facility. This tracking ensures that materials like lithium and sodium are accounted for, preventing environmental dumping and ensuring raw materials are processed and fed back into the infrastructure loop. The convergence of solid-state chemistry, AI routing, wireless roads, and bidirectional hardware changes the utility of the car. It becomes a mobile power plant, a self-aware node that stabilizes the global energy grid every time it parks.